Here we introduce the idea of power laws. Let's think about the degree of the nodes on the internet. Most internet nodes have low degree, meaning one or two connections. A few, called hubs, have very high degree. It turns out that the number of nodes with degree k follows what's called a power law. P of k is proportional to k to the minus alpha, 1 over k to the alpha, where alpha for the internet is about just a little over 2. So the fraction of web pages with k in links is about proportional to 1 over k squared. This idea of power laws turns out to be very powerful. Consider first the Gaussian or normal distribution of human heights. Heights are Gaussian distributed, meaning that the average value is pretty close to the most typical value, and the distribution of heights is pretty symmetric around the average value, and the ratio between the highest height and the lowest height is pretty small. By contrast, let's look at a graph of the population of cities. Most cities have a very small population, and a very small number of cities have a very large population. So the histogram is highly right skewed, meaning that while the bulk of the distribution occurs for fairly small sizes, this is US cities, most US cities have small populations, there's a small number of cities with a population much, much higher than the typical value, producing this long tail to the right of the histogram. This right skewed form is qualitatively very different from the histogram of people's heights. So power law distributions are right skewed, where a normal distribution is centered on a mean, a power law distribution is not. And power law distributions have a very high ratio of max to min. The largest city has many, many times more people than the smallest city, whereas the tallest human is not that much taller than the smallest human. Here's another interesting property of power law distributions. This right panel shows the histogram of city sizes again, but this time replotted with logarithmic horizontal and vertical axes. Now note that the histogram, when plotted in this fashion, follows a straight line quite closely. Distributions that follow a power law have the form some constant over x to the alpha, cx to the minus alpha, where alpha is the exponent of the power law. And if we take the log of both sides, we can see we end up with the equation of a line with negative alpha as the slope. Power law distributions occur in an extraordinarily diverse range of phenomena. In addition to city populations, the size of earthquakes, the number of telephone calls people receive, the frequency of occurrence of personal names in most cultures, the number of citations received by papers, people's net worth, a host of other variables all follow power law distributions. And here I'm showing some cumulative distributions of some of these phenomena. A power law distribution is also sometimes called a scale-free distribution. Why is that? Because a power law distribution is the only distribution that is the same whatever scale we look at it on. By this we mean the following. Suppose we have some probability distribution P of x for a quantity of x, and suppose it satisfies the property that P of b times x equals g of b times P of x. That is, if we increase the scale or units by which we measure x by a factor of b, the shape of the distribution P of x is unchanged, except for an overall multiplicative constant. Power laws apply to language as well, with a law called Zipf's law. Linguist George Zipf asked, how frequent is the third or eighth or 100th most common word? It turns out there's a small number of very frequent words in every language, like the or of in English, but lots and lots of rare words, like expressive or Jurafsky. Zipf's law says the frequency of the rth most frequent word is inversely proportional to its rank. So the most frequent word has rank 1, the second most frequent word has rank 2, and so on. And beta is close to unity, meaning that the frequency of the rth most frequent word is proportional roughly to 1 over r. that means that the most frequent word is twice as frequent as the second most frequent word. The most frequent word is 3 times as frequent as the third most frequent word, and so on. Power laws apply in economics too. The Italian economist Pareto was interested in the distribution of income. Pareto's law is expressed in terms of the cumulative distribution, the probability that a person earns X or more. And that probability, the probability that a person earns more than some value of X, is distributed as a power law as X to the minus K. The fraction I of income going to the richest P of the population is also a power law, usually expressed with the exponent eta minus 1. So if eta is 0.5, the top 1% gets 100 to the negative 0.5, or 10% of total income. In 2015, eta was 0.6, so the top 1% of the population got an even higher share, 16% of total income. So the higher eta is, the more inequality there is. Economist Thomas Piketty's book, which was #1 on the New York Times bestseller list in 2014, studies exactly how eta relates to the rise of wealth inequality. Where do these power laws come from? Lots of different processes can lead to them. There's not a single unique mechanism. However, there's been a number of interesting proposals. One commonly used mechanism is called preferential attachment, and it was proposed by Price in 1965 for citation networks. The idea is that a new citation to a paper is proportional to the number it already has. So if each new paper is generated with M citations, and new papers cite previous papers with a probability proportional to their in degree, to their number of current citations, we'll end up with a power law distribution for citations. So preferential attachment is one possible explanation. Preferential attachment is part of a class of models called rich get richer models. And these explain various power law effects. So citations, where we're drawing citations from papers that got previous citations, or assume cities are formed at different times, and that once they're formed, a city grows in proportion to its current size, simply as a result of people having children. That would lead to a power law. Or words, maybe people are more likely to use a word that is frequent, maybe just comes to mind more easily or faster, and that would lead to a power law. So in summary, many processes are distributed as power laws: word frequencies, citations, web hits. And these power law distributions have interesting properties. They're scale-free, they have a strong skew, they have high max-min ratios, and there are various mechanisms like rich get richer mechanisms to explain their prevalence. And they explain phenomena we've been dealing with all quarter: the use of stop word lists, so a small fraction of word types covers most tokens in running text, explains why a stop word list might be small. We've learned about power law distributions and their roles and properties.